Hello, everyone. On behalf of the Environmental Finance Center Network, welcome to our webinar, Fixed Film Secondary Wastewater Treatment Processes. My name is Kristen Crew from the Syracuse University Environmental Finance Center. Before we begin, we're going to go over a few logistics and then we can get started. During the webinar today, everyone will be kept on mute to ensure audio quality. If you have a question, please type it into the GoToWebinar question dialog box at any time throughout the session. We will be saving your questions for a facilitated Q&A session at the end of the presentation. After the webinar, you will receive a follow-up email that includes a link to the recording and other information that you may need. You can also download the slides from today in the Handouts tab in your GoToWebinar control panel. This webinar has not been submitted for pre-approval of continuing education credits. Eligible attendees will receive a certificate of attendance for their personal record. To receive a certificate for the session, you must attend for the entire session and register and attend individually using your real name and unique email address. Certificates will be sent via email within 30 days of the webinar date. If you have questions or need assistance, please contact smallsystems@syr.edu. Now for a little bit about us. The Environmental Finance Center Network provides training and technical assistance to small water and wastewater systems in all U.S. states and territories through our building technical, managerial, and finance capacity programs. If your community or utility needs assistance with drinking water or wastewater system management, please feel free to contact us through our request form, which I will be sharing in the chat very shortly. And on that note, we can get started. I would like to introduce our presenter for today, James Markham. He is a research scientist from the Southwest Environmental Finance Center. Welcome, James, and I will pass it right over to you.
Thank you. So let us get the slide switched here real quick. And looks like we are good to go. So thank you, Kristen. Thank you, everyone, for joining us today. As Kristen said, I'm James Markham at Southwest EFC. With me today to help with the moderation and Q&A is AJ Barney, another one of my coworkers. Today we're going to talk about fixed film secondary wastewater treatment processes. This is a category that encompasses quite a few different kinds of systems: trickling filters, rotating biological contactors, packed bed reactors, upflow reactors, etc. But we're going to really be focusing primarily on trickling filters and RBCs, or rotating biological contactors, because those are the most common types of fixed film processes that we have in the US. And of course, given the limited time we have, it's not going to be an exhaustive description of these processes. It's meant more to be an overview, describing the processes, providing some history, some design characteristics and efficiency, some basic O&M information, a little math related to the treatment processes, and the parameters that you need to keep track of when operating a fixed film process. But first, since not every treatment system, wastewater treatment plant, has one of these, let's start with a definition. What do I mean by fixed film? So fixed film refers to a film of microorganisms treating waste and living in solids or slimes or biofilms that are attached or fixed to a media or substrate in the treatment process basin. This differs from activated sludge processes in that in activated sludge, the microorganisms doing the work are essentially free floating in the treatment basin with all the nutrients and everything else, whereas in a fixed film process, the microorganisms are for the most part attached to and resident on a media that's in the basin. It's actually one of the oldest forms of wastewater treatment process. We have the role of aerobic microorganisms in wastewater treatment was first recognized in around 1890, and it was discovered that, hey, we can actually farm bacteria essentially as part of a treatment process. It's a biological treatment process. I think it's actually probably more analogous to ranching, because what we're essentially doing is feeding bacteria organics in the wastewater while providing a home for them on the media that gives them access to oxygen from the air, food from the water, and then the microorganisms then use the organic material in the water stream to grow and multiply. Their metabolism is essentially treating the water by converting waste into new growth and carbon dioxide. And then we periodically cull the herd, so to speak, to maintain the growth of those biofilms at a specific desired rate. The two types of film process that we're going to talk about today, again, as I said, are trickling filters and RBCs, and we'll start with trickling filters, or biofilters, or biotowers, as they're sometimes known, depending on their shape and the media that they use. It is worth noting from the start that trickling filter is kind of a misnomer. They don't actually physically filter wastewater in the sense of straining materials out like a coffee filter. They're, as I said, removing unwanted organics from the wastewater through metabolic processes, not physical filtration. But these were the most widely used form of wastewater treatment in the first half of the 20th century. It's kind of sort of the first large-scale public treatment systems used trickling filters. They were in use in Madison, Wisconsin in 1912. There was one in Reading, Pennsylvania in 1908 that had a 2 million gallon per day capacity. So, you know, where the first large scale public treatment system was kind of depends on your definition of large scale. But the point is they've been around for a very long time, and they still are in a variety of applications. And not just in wastewater. You know, if you're an operator who's never actually seen one of these in a wastewater treatment plant, there's a good chance you might have actually run across one in a pet store or in an aquarium. What you're looking at here is essentially the hobbyist version of a trickling filter. And although from a design perspective, it's set up a little differently than what you would see in a wastewater treatment plant, it has the same basic components. So from a simplified version, this is actually not a bad thing to look at. You've got a water distribution system that sort of spreads the inflow over a filter media. In this case, it's plastic bioballs, and you can see for their size, these have a very high void space and relatively high surface area for the volume that they occupy. That's where the bacteria live. They treat the water as it passes by eating the organics that are in it. The water trickles through, is collected on the bottom. There is going to be biomass that sloughs off of this because, again, it's metabolic processes. We're feeding and growing bacteria, and they have to go somewhere. So they're collected at the bottom of the process. And in the fish tank version, you essentially got that sponge there keeping those organics out that you would periodically clean in a wastewater treatment plant. You'd have a secondary clarifier at the end of this process to handle those solids that are sort of continually coming out of the process. You may have also seen something like this, you know, in a park that has maybe a large pond or something like that. This is also a trickling filter. Water is being pumped up this pipe into these beds that have media in them. Bacteria grow on it, and they treat the water as it moves through. So they've been around for a long time. They're still around in a lot of different applications, but the process for all of these is more or less the same, although the details vary. You're typically going to have aerobic and facultative bacteria in there, so aerobic bacteria living where there's only enough oxygen for respiration, facultative bacteria being ones that can use dissolved oxygen or get oxygen through other means, and therefore can live in aerobic and anoxic and anaerobic conditions. But trickling filters generally involve BOD removal in aerobic conditions and can also achieve either BOD removal and nitrification, or just nitrification in the presence of oxygen under the right circumstances. You can do both of those in the same system, in the same filter. In some cases, depending on the biological loads and the hydraulic loads, those will be done, those two processes will happen in different stages. If they are happening in the same filter, generally what's going on is heterotrophic bacteria, which are fast growing, are outcompeting the nitrifying bacteria at the top of the filter where the most food is available, and they're doing the BOD removal up there, and the nitrifying biomass grows in the bottom half of the filter. But again, the ability to do both of those processes in a single filter, and the efficiency of the nitrification process really kind of depends on loading rates. They have to be relatively low, and that's something we'll discuss a little bit further on. The initial design of trickling filters looked something like this. They tended to be rather large. This is one in Birmingham, England, covers 30 acres in 1 to 3 acre beds. You've got a layer of stone in there that is housing the microbes, and you've got a very elaborate sprayer system on top of it that's just trying to distribute the wastewater evenly over the media. Water's treated as it trickles through and gets collected in an underdrain, which you can't see there. One of the things they noticed early on was that you could use just about anything as a substrate or a media for the microbes to grow on. Wood, stone, bricks, slag, kind of didn't really matter as long as it was relatively small and relatively uniform, sort of in the 2 to 4 inch in diameter range. The whole idea was it had to have enough surface area for the microorganisms to grow, and there had to be enough room for water to pass through, and it had to be porous enough to allow for airflow. So it's a really relatively low-tech, low-maintenance approach, and was one of the first approaches that was used for BOD removal and nitrification of wastewater. Sort of about the same time or shortly thereafter, activated sludge was also developed. This is an experimental plant around 1913 in Brooklyn. You can see that although this is all made of wood, it's very similar looking to what we have in modern times. And activated sludge kind of outshined the trickling filters, because it had some advantages. You could use a smaller footprint. Quite often you got better effluent quality, lower nuisance factors. One of the issues that they had with sort of particularly these large scale open trickling filters was, smells and bugs and things like that, which you could control a little bit better in an activated sludge system. But, they both, through the first half of the 20th century, remained viable options. Here's some sort of comparisons between a trickling filter and an activated sludge process. And you can see they both get rid of suspended solids, they both reduce bacteria, they both reduce BOD and nitrogen. But as I said, activated sludge systems kind of became dominant mid-century, and the use of trickling filters declined. But they continued to be used because, again, they're sort of low-tech and they fit a lot of applications. And in sort of the middle of the century, and around the 50s, lightweight synthetic media started to be developed that could replace rock as a media in trickling filters. And that really increased the capacity of existing trickling filters, allowed design to be changed so that they would have higher capacity and could meet the ever higher effluent standards that have been developed. So they continue to be a really relevant treatment method. And in some cases, treatment systems actually use both trickling filters and activated sludge processes to get the best of both worlds. So this was kind of the original design, large field sprayers over the beds. And basically in a situation like this, you're essentially relying on the distribution of the spray grid and the piping network to ensure that you get uniform distribution over the filter, because the one thing you want to do is keep it wet and make sure that the load is evenly distributed. Wasn't too long after those original versions were developed where you were essentially, again, we're relying on that fixed nozzle system and the pumping distribution system to make sure the distribution was even, that somebody came up with the rotary distribution arms, which basically spin around in a circle in one place and use the rotating speed of the arms to sort of ensure that the distribution is even. You can control the motion of the arms simply by changing the volume of water that's coming out of them. And although I'm not showing it here, there's actually usually sprayers on the leading edge of the arm pushing in the opposite direction, and you can use those to control speed. So sort of on the sort of low-tech side of things, you could actually have a rotating distribution arm without actually having a motor to run the process. The water pressure alone would control the rotational speed. And I do want to point out that although this is spinning rather quickly here for illustration purposes, normally these turn at about 1 or 1.5 RPMs. They're moving relatively slowly. So, two different ways of getting to the same idea. The goal here is uniform hydraulic loading over an area for optimum efficiency. With a fixed spray head, you use the pattern to do it. With a rotating arm, it's essentially moving around in circles and distributing the water that way. Some downsides to the fixed spray head side of things. The piping requirements are pretty extensive. You have to have a pretty involved pumping system for even distribution. And of course, that's a lot of pipe to maintain and repair, and access is somewhat difficult. Whereas with a rotating arm, it's all a little bit more localized. You don't necessarily need a motor, although you do need a pump. Because you can use the force of the wastewater flowing out of the distributor arms to kind of control the speed, although many systems now have motors on them as well, as a way of dialing in the exact rotational speed that you want. And there's a few reasons that you would want to do that, which we'll talk about in a minute. So this is kind of what the typical trickling filter in the US looks like, at least if it's one of the older designs. You got a bed of media. You've got water coming in at the top, flowing through the media, being treated on the way down, collected at the bottom. This one happens to be in Brazil, but this is more or less the rotating arm design. Although I do want to point out that the scales can be vastly different. This one is probably about 10 feet tall. This is one in Stockton that is used particularly for nitrification, and you can see relative to these trucks over here how big this rotating trickling filter actually is. They can be enormous. This one is obviously motorized, but regardless of scale, in cross section they look basically the same. This is what they look like. You've got a distribution arm, you've got a pipe feed going to the center, you've got a filter media that's in some sort of a containment system. There's an under drain collection system, underneath it that allows the water to be collected and moved on to the next process. So there's 4 main critical components: the media, the distribution system, the containment structure, and the underdrain. And then of course there's going to be auxiliary equipment like a filter pump, a secondary clarifier after this to deal with the solids that inevitably are going to come out of here, because again, you are growing bacteria. It's got to go somewhere. So there's going to be a continual sloughing of the slime layer that you have to deal with. In an established trickling filter, that layer could be up to 1 centimeter thick, but it's just the top layer that's really doing the aerobic work. So you have to slough that off periodically, either through increasing the rate that water is moving through it, or reducing the amount of food that it's getting so that it doesn't grow as fast. It's also worth pointing out that in addition to the aerobic and facultative bacteria that are growing in there that you want, all sorts of critters like fungi and algae and worms and insect larvae and snails can grow in trickling filters. So although they are low tech and low maintenance, they're certainly not no maintenance, and you have to pay attention to operational parameters to make sure that those sort of macrofauna don't gum up the works, so to speak. So let's talk a little bit about the filter media. The house that we're providing for the bacteria. This is another example from the UK, but it's showing rock media essentially. It's got primary effluent being sprayed over a coarse gravel that is providing the home for the bacteria that are doing the BOD removal and the nitrification. Rock media doesn't tend to be used anymore. Its original design, this is sort of the original way these things were designed. Typically, it kind of doesn't matter what kind of rock it is, as long as the size is relatively uniform. So you'll see legacy systems out there like this one with rock that's anywhere from 1.5 to 4 inches in diameter. One of the main sort of capacity limiters with rock media is that it's heavy, it's got limited void space for ventilation, and it's got a limited surface area for the volume that it occupies. Void ratio basically tops out at about 50 with rock. And I think that's one of the reasons that activated sludge kind of overtook trickling filters, because although they are relatively easy to run, there were some capacity limitations for these. In the 1950s, synthetic media started getting developed. So essentially plastic media to replace the rock, engineered media. And that provides a lot of advantages over rock in that you can engineer specific surface areas for specific types of microbial growth. You can engineer specific void spaces for airflow. It's uniform, so it enables even loading distribution. which sometimes you don't get with rock. And it's really light, so it's easy to install, it's easy to handle, and you can have much deeper beds because the underdrain support structure does not have to support so much weight. So, in the same footprint, you can treat a lot more wastewater with synthetic media than you could with rock in the same basin. I do want to point out that the looks are a little bit deceiving here. The figure on the left, the random dump filter media, which is kind of a direct replacement for rock, those are typically like 1 to 4 or 5 inches in diameter, whereas the box on the left, that sort of Lego-looking brick, is actually about 2 feet by 4 feet by 2 feet. So they're significantly different sizes, but those different approaches have some really interesting advantages because the differences in media characteristics allow for, as I said, a lot more surface area with plastic media. You can get a much bigger void ratio, so you can feed more oxygen in there. And again, it's significantly lighter on the, an order of magnitude. And what you're looking for here, ideally, is lightweight, high surface area, high void ratio, so that you can effectively both farm your biofilm, but also provide room for it to breathe and slough off, and so that the filter doesn't get plugged. Rock isn't really used in new installations these days, but there still are a lot of legacy systems, like some of the ones I showed you, that are out there that work just fine, that they meet the capacity that they're required to. But one sort of common element with trickling filters that use rock as a media is that they're typically very shallow, because the underdrain has to hold up very heavy media. So they're typically only about 5 to 7 feet of media in a basin that's maybe 10 feet tall. Random media, as I said, is sort of the go-to retrofit, where you can essentially replace the media, get higher capacity and better water quality coming out of your process without actually changing the entire basin. So that sometimes works. New designs, new construction typically use those blocks, the vertical and cross flow media. They can be a lot taller because one of the advantages of that form factor is that they're essentially self-supporting. So you don't need a giant concrete structure to hold everything in. You can use a lighter weight containment structure, and some modern trickling filters using vertical and cross flow media are as tall as 40 feet, where the top 25 feet is media and the bottom is under drain and ventilation. Quick points about the vertical and cross flow media. They have somewhat different applications, although they're sometimes used in the same filter. Vertical media basically has the channels going straight up and down, so the water moves through them fairly quickly, and you've got higher shear forces. Those are typically recommended for high BOD loading applications. Cross flow, which is what the actual picture was in the previous slide, has sort of zigzag channels at 60 degrees or so from the horizontal, and they provide a lot more turbulence than a vertical flow does. And that works better when the loading rate is in sort of the low to medium range. Although those two are actually often used together in sort of multi-layer pancake form, where the top layers will be cross-flow media to sort of evenly distribute the water to the vertical flow media that's below it, that it runs through. The funny thing about the sort of different medias and the different design is you can often tell what's inside a structure just by looking at it from the outside. Older systems are, again, typically short, 10 feet or less, made out of concrete or brick. They probably had rock media in them at one point, although they may have plastic media in them now. Typically these days, if you see something 20, 30, 40 feet tall, it's probably got that block form vertical and cross flow media in it. And again, because it's self-supporting, you don't need the really heavy duty concrete containment structures. You can have sides that are made out of steel or fiberglass, because again, they're containing, not supporting really the media that's inside. So that's the containment structure. Obviously, the bottom of this will have a fairly sophisticated underdrain system, which is essentially usually a concrete slab, some sort of drainage system in the bottom to collect the water and the sloughed off biofilm with a grid that's porous that is holding up the media above it. There's a lot of different kinds of material that can be used. They're kind of design dependent. The But the goal of this is to essentially suspend the media up off the base of the structure, provide a path for air to come in, because again, these are aerobic processes that we're talking about. And it is important to point out that underdrains can be big. In some of the larger ones, they can be 10, 15 feet tall, but they are confined spaces, so they can be a little bit dangerous. And we had a safety training not too long ago talking about confined space procedures. That's something you want to pay attention to if you have to go into the underdrain system, which you probably have to do on an annual basis for cleaning. Basically, this is the way the air gets in and the water gets out. There are sort of two different ways that airflow can be managed in a trickling filter. Some just use natural ventilation, where basically the differences in temperature between the water and ambient air are causing the airflow. But a lot of systems are also supplemented with mechanical ventilation because it gives you more control over the airflow in the system. Because physics is physics, and particularly if you're in a place where there are significant differences between summer and winter temperatures, the airflow pattern will actually change. So in the summer, the ambient air is warmer than the water moving through the filter. So the air in the filter gets cooled down by the water, it sinks and it draws warm air in from the top. So you'll get a top to bottom airflow. And in winter, that process reverses. You'll get a bottom to top flow because the water is warmer than the ambient air. So as one of the operational parameters that you need to keep track of is dissolved oxygen to ensure that there's enough oxygen for the aerobic bacteria to do what they want. This change in flow can sometimes throw a little bit of a wrench in the gears, which is why a lot of systems, even a lot of older design systems, have been supplemented with mechanical ventilation systems to basically have a better control over this. So that's sort of some basic physical parameters. Let's switch gears a little bit here and talk about some design characteristics and efficiency and the parameters that you need to keep track of to make sure that your trickling filter is running correctly. Two important ones are the organic loading rate and the hydraulic loading rate. Trickling filter performance depends obviously on design, but also system operation control. You've got bacteria that are responsible for the treatment, and they're feeding on the organics in the water. You have to balance all of this to control growth. And of course, you have to balance the ambient temperature as well, particularly if you don't have an air system. So you've got to monitor the food in the water that's being supplied to the bacteria so that you can control the growth rate and therefore the growth rate of the biofilm. You don't want to starve them or overwhelm them. And wastewater, of course, comes in a variety of concentrations, often different concentrations at different times of day. But the water also has a mechanical action on the biofilm. Greater flows can wash more biofilm out. Low flows might lead to excessive biofilm buildup, which can then lead to clogging and ponding and anaerobic conditions and odors and all sorts of growth of undesirable organisms. So these two parameters here are sort of those two main parameters that we're talking about. The organic load rate is basically the food side of things, how much organic matter is being fed into the system relative to the media volume, which is typically expressed as pounds of BOD per 1,000 cubic feet of media normalized. And then the hydraulic loading rate is how much water is actually moving through the filter per day in relation to the media's surface area. And that's going to be expressed as gallons per day over feet squared. I'm going to show you a little bit of math here. But it also is important to recognize that you can get high loading rates with high concentrations and low flow, or vice versa. So let's step into these two parameters a little bit. This is the formula for the organic loading rate per day. I don't expect you to memorize this, but I do want to point out that you're basically looking at the influent flow rate, you're looking at the BOD concentration, and you're looking at the volume of media in the system normalized. So it's quite a complicated formula because we're using mixed imperial and metric units, and we've got to have some conversion factors in there. So there's a simplified version of this, but the point here is that there's sort of three parameters that you're looking at: volume, flow, and BOD concentration. It's really important to note, though, that when you're calculating this, you really only want to take the concentration of the primary effluent that's flowing into your trickling filter into account. I'm going to talk about recirculation in a minute. A lot of systems have recirculation for a lot of different reasons, but when you're looking at the organic loading rate, you don't want to include that in the flow. So sort of looking at a schematic of what this system would look like, you would have, primary effluent flow coming in, being joined with a recirculation flow, and both of those are going into your filter media, and then the effluent is coming out. Some of it's being recirculated. For organic loading rate, the things in blue are what you're concerned with. The effluent concentration, the BOD concentration, which you're going to get from sampling, the volume of that flow that has that concentration, and the volume of the media in your system. Because if you included the recirculation flow, you'd actually be significantly overestimating the mass that's moving in there, because sort of the assumption is that most of the BOD moving out is going to have already been treated. So if you added this flow in and multiplied that times the concentration, you'd actually be overestimating the amount of BOD that's moving into the filter, assuming everything is working correctly, of course. The other piece of the pie, or another piece of the pie, is the hydraulic loading rate, where we're basically relating the volume of water moving through the filter to the surface area of the media. And if you have recirculation going on, in this case, you actually do want to include it, because you're just looking at the water flow, not the concentrations of waste in it. So this is a lot simpler formula. It's just basically the flow in plus the recirculated flow divided by the surface area of the media. So not the surface area of the tank itself, but the surface area of the media inside it, which is going to be significantly higher. Again, looking at it from a schematic point of view, the pieces in blue are what you're concerned about here. You do want to include that recirculation flow, which kind of begs the question, what about recirculation? Why do we have that? What's important about it? Because I kind of referred to it without explaining directly why you might want to do that. Recirculation is often critical to the operation of trickling filters, because it allows for operational flexibility, because you're essentially decoupling that organic loading and the hydraulic loading. If you don't have recirculation, the concentration that's coming in is the concentration that's coming in, which you can control by the speed that you're pumping in, but there's a direct relationship. If you're recirculating, you can break that relationship or decouple it so that you can adjust biological loads and hydraulic loads separately. And you want to do that for a lot of different reasons. Biomass is continually growing in the system, so you have to shear some of it off. So you can use recirculation to produce hydraulic shear by increasing the volume that's moving through to slough solids off. You might do it to dilute wastewater to lower BOD concentrations. For example, if you've got a higher concentration coming in than your filters designed to handle, you could use it to dilute toxic waste, increase contact time by essentially just sending the water through a second time. You can often will increase hydraulic loading rates to reduce flies and snails and other nuisances, to essentially flush them through the system. You might do it to receive the filter with microbes, because again, that recirculated water is going to have some sloughed off microbes in it. To help with uniform distribution of the flow throughout the day, preventing the filters from drying out, to return dissolved oxygen to the top of the filter if your airflow has changed, or just to match hydraulic loading rates to the recommended specs for plastic media. If you're retrofitting rock to plastic media, chances are it's going to require a higher hydraulic loading rate. So part of that retrofit may involve the inclusion of a recirculation system. The parameters for recirculation are going to be design specific, but they're usually looked at as a ratio. So TF stands for trickling filter, and it's essentially just the recirculated flow rate divided by the non-recirculated influent flow rate. So if you had 10 million gallons a day recirculated flow, and an influent rate of 5 million gallons a day, you'd have a recirculation ratio of 2. That's a parameter you would want to keep track of, because your designs would have a range that you would want to stay inside. Another related parameter that you'll want to track that's related to recirculation or often controlled with recirculation is the dosing rate or Spülkraft rate, which is German for flushing or rinsing rate. This is kind of a weird parameter, but it's important because it's used to control the biofilm thickness. This is the culling part of the microbranching that I was talking about in my goofy analogy at the beginning. So this parameter quantifies the intensity at which influent and recirculation flow are being applied to the filter. And increasing this rate basically lets you rinse or shear more biofilm off the media to maintain desired thickness. And again, you need to do this because it's an aerobic process, but oxygen and food can really only get into the very top, millimeter or two of the biofilm. So if it grows too thick, there's going to be anaerobic action going on underneath. And so there's really not a reason to have really thick biomass. So you control that by increasing the dosing rate. And it's kind of a weird parameter. It's inches per pass, but basically you're looking at the hydraulic loading rate and dividing that by the number of arms and the rotational speed and time. And just to kind of give you an idea of how this plays out, typically your filter will be designed to run at a specific dosing rate based on the organic load. So for example, that second line there, an organic load of 50 pounds of BOD per 1,000 cubic feet per day. In normal operations, it's going to have a dosing rate somewhere in the 2 to 6 inches per pass, but periodically you'll essentially increase that to flush some of the biofilm off. It typically gets done once a day, might get done every couple of days, or depending on your specific system. But you can see how you're essentially increasing the dosing rate to the high end of normal operations to make sure you flush some of that biofilm off and maintain it in the way you want to for optimal operations. Last but not least, we've got removal efficiency. Obviously, you need to know what's going in and what's coming out. Relatively easy to calculate. It's the BOD concentration, nitrate concentration going in, minus the concentration going out divided by the in. So that'll give you the removal rate in percentage. So those are kind of the big deal parameters that you're going to keep track of. You're obviously going to have to track other things via sampling that we'll talk about as well, like dissolved oxygen and things like that, to make sure that things are working correctly. But those are some of the big parameters that you're going to pay attention to. You can operate trickling filters a variety of different ways. As I mentioned, you can do a two-stage operation where you're essentially separating the BOD removal process and other processes like nitrification into separate tanks, or you could do those potentially in the same tank if the flow rates and the loading rates are low enough. And you get sort of this pancake effect where under the right conditions, you've got the BOD removal bacteria working on the top and the bacteria that are doing the nitrification on the bottom, where there's less food and they're slower growing. So you can operate two-stage, single-stage. Generally, you're going to do one or the other. You can also operate these things in series or in parallel. So series operation is one after the other. You've got primary effluent coming into a trickling filter that's doing its treatment process, and the effluent from that is moving on to a secondary filter. So, the two-stage operation is essentially a series operation, but you could actually use series operations for BOD removal, for example, where the first trickling filter is handling the bulk and the second is acting as a polishing filter. Or you could run them in parallel, where you're essentially distributing the primary effluent to different trickling filters, and they're essentially getting the same concentrations. So just to put some numbers to this, if you were had 1,000 pound per day load and you're running in series and your first trickling filter has an 80% efficiency removal, well, the first filter is going to deal with the first 800 pounds of BOD and the water going to the second filter would only have 200 pounds of BOD per day to deal with. So it would essentially become a polishing unit. And that might allow you to have a greater overall removal rate. Running in series reduces the risk of short circuiting and partial treatment, might enable you to better control biofilm thickness because you can sort of dial in the loading rates and the hydraulic rates that the two filters receive. Of course, if you're running in series with that same 1,000 pounds per day, like we're showing here, each of them is going to get 500 pounds at 80% efficiency. There'll be 100 pounds left over coming out of each of those trickling filters at the end. There's advantages and disadvantages to running them both ways. As I said, you run things in series, you're less likely to short circuit and have partial treatment. If you run things in parallel, it makes operations and maintenance a little bit easier because you could actually take one bank offline and do work on it and still be treating through the other line. So there's different ways that you can run these. It all really kind of depends on the design parameters and the loading rates of the water that you're treating, which brings us to our next topic, which is filter classification. Trickling filters are typically classified a couple of different ways. One way is based on the applied organic loading rates that they're designed for, or the type of treatment that they do. So in terms of organic loading rates, it's kind of broken into three categories: low, intermediate, and high. And I'll get into exactly what that means here in a second. You can also have filters classified as just doing carbon oxidization, BOD removal, carbon oxidization, and nitrification, so BOD removal and ammonia conversion to nitrate, or nitrification only. Low rate filters, as I'll show you in just a second, can actually typically do both carbon oxidization and nitrification and it's generally because the load rates make them good places for the slow growing nitrifying biomass to live. Intermediate and high rate filters can do both, but typically they're set up to do one or the other. Higher rate filters handle higher organic loads and higher hydraulic rates, that they typically have lower BOD removal efficiencies. And then you might actually describe the filter based on what it's doing. So, whether it's like a nitrifying only filter or a roughing filter, which is essentially sort of a first stage trickling filter that might be used in front of other trickling filters, or maybe an activated sludge process. So let's look at some of the design characteristics of these various type of filters and what kind of media would be used. Low rate filters, basically we're talking about organic loading rates of 25 pounds per 1,000 cubic feet per day or less. These are typically sort of the older school designs where you've got 3 to 8 feet deep of media. You will notice there that with the plastic media, you've got a much higher hydraulic loading rate requirement because there's more void space there. So you will often have extra circulation going on there. But regardless of which kind of media you're using, you get pretty high BOD removal rates in the 80 to 90% range, and you typically don't need a secondary combined process or combined secondary process because you're doing the nitrification in the same basin. Although if you have tertiary requirements, you're going to need additional processes. The intermediate rate filters are the sort of 25 to 40 pounds of BOD range. This can be done in sort of the old school design or the newer designs that tend to use the cross and vertical flow media, the taller support structures. Again, there's a pretty significant difference in hydraulic loading rate, but because everything's moving through a little bit faster and the BOD rates are higher, you typically get a lower BOD removal rate. You can still have both nitrification and BOD removal going on in these systems, but it's less typical. And once you get to the high rate filters, which are those designed for the 40 to 100 pound range, or the high end, you've got high hydraulic loading rates and significantly lower BOD removal rates. And typically you're going to have a secondary treatment dealing with nitrification because the first one will just be dealing with BOD. As I said, you can design these filters or can categorize these filters based on what they're designed for. There's something called a roughing filter, which is essentially a trickle filter that is designed to let a lot of the BOD go through the system. These are typically first stage biological treatments that are going to happen before an activated sludge basin or a rotating biological contactor, which we'll talk about here briefly in a second, or maybe another small trickling filter. And then you can have
filters that are designed specifically for nitrification. Those tend to be the newer designs, the big ones with very high hydraulic loading rates, but they can get rid of a significant amount of ammonia and convert that. Regardless, the nitrification removal is pretty high in a lot of these, in the 75 to 95% range, assuming that the flows are set up correctly. But again, you can only do this in a single filter with lower rates, typically lower rates, and that's because that allows these heterotrophic bacteria to live in the upper part of the filter and the autotrophic bacteria that are doing the nitrification down in the bottom. Of course, I said these are low tech, low maintenance. That doesn't mean they are maintenance free. You have to do a lot of sampling to verify that your parameters are being met. I'm not going to go through all of these. I just want to point out that ranges vary depending on design. And the different parameters are going to be sampled at different rates. Some stuff you're going to look at daily or weekly. Chemical oxygen, dissolved oxygen, temperature. These are things that you need to keep track of so that you can monitor the efficacy of your system. There's going to be parameters running outside these ranges, so it's important to understand your system, have troubleshooting guides, and recognize that, for example, if you've got high TSS concentrations coming out, it's probably due to one of 4 principal factors, something like high hydraulic loading or short circuiting through the process. Heavy sloughing of the filters, in other words, there's too much biomass. It might be caused by shock loading, might be caused by gasification because you've got anaerobic conditions going on in there. There is sampling requirements. They are low maintenance. They are not maintenance free. And you're going to have issues that you're potentially going to have to deal with, and you're going to have to understand how to deal with those. So, odors is an issue, or can be an issue with trickling filters for a variety of causes, septic influent, excessive organic loading, anaerobic conditions, bad ventilation. But for every problem, there is a solution that you can apply. Same thing with filter ponding. It's another thing that happens. If you've got excessive growth, the filter media will plug up and you end up with uneven distribution. That kind of thing promotes the growth of snails and moss and algae. You can have filter clogging in an open filter if you're in a place that has a lot of leaves because debris accumulates on the top. So you're going to have to monitor these things and make sure that they're being cared for correctly. And again, O&M processes are going to happen on daily, weekly, monthly, seasonal schedules. You have to pay particular attention to the mechanical components as well, making sure that your rotary distribution system is running smoothly, that orifices aren't plugged, that the rotational speed is right, that the arm levels are correct, and you'll probably need to periodically do pan tests just to make sure that the wastewater is being evenly distributed. So somewhat longer explanation of these things than I wanted to have, but there's advantages and disadvantages to using trickling filters. Some of the advantages are that they have low energy requirements, relatively low maintenance requirements, and they've got the ability to treat variable organic and toxic loads, particularly if you've got the ability to recirculate. Some of the downsides, you can have issues with odors, you can have issues with microfauna. They are temperature sensitive. It's a biological process. If you're in a place that has significantly cold weather, particularly if you don't have a motorized system, they can ice up. And if you don't have a motorized system and you have low flows, your distributor arms theoretically could actually stop turning because there's just not enough pressure. There's advantages and there's disadvantages to them, but they play an important role in wastewater treatment, and there is a place for them. So that's a very quick and dirty explanation of trickling filters. We're going to ask a couple of poll questions. Kristen, why don't we just do the first 2, just so that we can verify everybody's here and paying attention. And then we'll go on to a short description of rotating biological contactors, which are essentially the same process, but different mechanics.
All right, so here's that first question. Fixed film processes are what kind of treatment process? A primary or a secondary? And get those answers in. I'll be closing the poll in 3, 2, 1. All right, James, looks like 72% of people got the answer correct with secondary.
Yep, it's a secondary process. You're going to need to have some sort of primary sedimentation process in front of this because you don't want to clog up your filter with grit and dirt. So.
And the next poll question, which trickling filter media is likely to have the greatest surface area for a given volume? Rock media, random plastic media, vertical flow media, or cross flow media? And get those answers in. I will be closing the poll in 3, 2, 1. All right, it was tight. So 39% of people went for B, random plastic media, and 39% of people went for D, cross flow media.
The correct answer is cross-flow media, but because there's so many different ways you can engineer this, there is actually quite often a significant amount of overlap between the different types of plastic media. So we'll pretty much accept, B, C, or D for that. But generally, the media that has the most surface area per volume is a cross-flow media. All right, so let's take about 10 minutes and talk about rotating biological contactors. Much of what we discussed relating to trickling filters applies to them as well. It's a secondary biological process. We're basically farming microbes. We're just doing it with a slightly different mechanism. With a trickling filter, the water is moving over the media. In a rotating biological contactor, the media is moving through the water. So similar biological process, similar outcomes, different mechanism. The early ones looked kind of like this. The one on the left there is from 1950. They were developed in the 50s. You basically got a central shaft with rotating plastic media on them. Different discs together are called a drum. Those are submerged about 40% in the wastewater that's being treated. There's a motor drive assembly to turn them. They typically spin at about 1.5 RPMs so that the microorganisms that are growing on the biofilm are alternately exposed to food and water and oxygen in the air. Same process is going on. Microorganisms are absorbing the nutrients, they're growing, they're forming a biomass, they're sloughing off. As is the case with trickling filters, you're essentially cleaning the water by farming microorganisms. These are typically used in relatively small facilities, treating waste from maybe 50 to 5,000 people. They're sometimes part of package plants. They got a little bit of a bad rep in the United States. They were first developed in the 50s. They got really popular in the 60s and 70s, but the earlier ones had a lot of design flaws, mostly with regard to the filter media, so they kind of fell out of favor, but innovation has continued, and they continue to be very popular around the world, and they're used a lot more here in the US these days as well. Again, here's another schematic to kind of give you a side-end view and a front view of what these things look like. You've essentially got a trough of water with a bunch of discs rotating in it. It's not too much different than actually one of those front opening washing machines in a way. The process will look something like this, where you've got preliminary effluent coming into a preliminary clarifier, and that'll be running through one or more trains. There's not always 4 in place, although that is a fairly common number. You may run these in series, you may run them in parallel, but they have the same process going on, but slightly different components. They're typically going to have a concrete or steel tank with baffles that you can sometimes remove in between the different shafts. It's going to have the filter media on the shafts, some kind of cover typically to protect them from fluctuation, particularly if you're doing nitrification, because those are very temperature sensitive. Bacteria, there's going to be a drive mechanism, there's going to be piping in and out, there's going to be a secondary clarifier on the outside end, and although it's not shown in this diagram, there's often an under drain in the tanks to remove any solids that might settle out in the tank. The media is plastic, but it tends to have some slightly different characteristics, and they're classified differently. You have standard density and high density media, and that is basically related to the surface area that's on the shaft. So the standard density are in the sort of 100,000 square feet per shaft range, whereas a high density could be up to 165,000 square feet. The most common use for standard density shafts is BOD removal or combination BOD removal and nitrification. If you're just doing nitrification, it tends to be done on a high density shaft. One of the other differences between trickling filters and these filters is that the biofilm thickness is significantly thinner, the optimal thickness. And part of that has to do with the fact that these are rotating, there's a mechanical action going on. And if you let the biofilm grow too much, things get out of balance. It puts a lot of wear and tear on the bearings and the drive mechanisms. And you can look at that bottom row there, the percent of weight that's occupied by the biofilm is sometimes up to 80% of these things. It's really important in RBCs to keep the biofilm at thin to work optimally, whereas there's a little bit more flexibility with a trickling filter. They can be really huge. This is actually a smaller one. Largest shafts are typically about 27 feet long, maybe 25 feet of media or so, but they're big drums, and you can kind of see the layers of plastic media that are sitting there, and this is what they would look like, installed. They're typically in some sort of a housing. This is two different basins. I think they're doing nitrification in one and BOD removal in the other. But you're basically focusing on the same parameters for an RBC as you would for a trickling filter. You've got to monitor and maintain specific loading rates, hydraulic rates, loading rates. Obviously, removal efficiency is important. As the diagram showed, recirculation is usually a factor in these as well for some of the same reasons, shearing off excess biogrowth, etc. And like trickling filters, you can do BOD removal and nitrification in the same contactor if the conditions are right. This picture actually shows, you can sort of see a color gradation from beige on the left to brown on the right. And what you're seeing there is a slow transition from carbon metabolizing bacteria on the left to the nitrogen bacteria, metabolizing bacteria on the right. And again, with the proper influent conditions, you can do both. But again, you've got to pay attention to things like alkalinity, temperature. It's got to be a low BOD. Trickling filters generally work with very low BOD loading rates to begin with. And pH is really critical as well for the nitrifying bacteria. You have to keep things in sort of the 6.5 to 8 range. But if you do that, you can reduce ammonia nitrogen as well in these. So some parameters that are related to RBCs, wastewater sources. If you're just doing primary BOD removal and or BOD and nitrification, you're going to be using primary effluent nitrification only. If you've got a stage system, that's going to be secondary influent coming out of a BOD removal process. Different densities that are typically used for those. But the thing to point out here is these bottom couple of rows. The organic loading rates for effective use of RBCs are significantly lower than for trickling filters. The range for even a low rate filter is up to about 25 pounds of BOD. You're more or less maxing out at 6 pounds of BOD for the first stage, and you would want an average of about 3 to 4 for one of these to work. So again, this is one of the reasons that they're more applicable to smaller applications. Loading rates are also significantly lower on the hydraulic side as well. So you typically have higher retention times, but they do the same process and they can be operated the same way. You can do treatment trains in a single train. You can have parallel trains for the same reasons that you would do that with trickling filters. One of the unique features of RBCs is that they are often designed with different flow. Sometimes they're designed with the flow going parallel to the shaft, and sometimes they're designed with the flow going perpendicular to the shaft. And that basically depends on treatment requirements. If the flow is running perpendicular to the shaft, then the initial load gets distributed to a bigger biomass because it's sort of hitting it side on rather than straight on. So there's different reasons for using different formats. You can also run them as single stages or 2 stages, where you've got everything in one basin, or you've got different processes happening in essentially different subdivided basins using baffles. And that can be the case whether the flow is going perpendicular or straight on to the shaft. pretty obvious from the earlier slides that there's some limitations with our RBCs. Lower organic rates and hydraulic loading rates are the primary ones. They don't really provide as much flexibility as trickling filters when it comes to operating over a wide range of organic loads, and they cannot be used as roughing filters or high rate filters because they just can't handle that kind of flow. But again, they're really useful, and they're a really good option for smaller communities where there's not a high load of BOD and ammonia that needs to be treated. Again, these are not maintenance free. There's a different set of tasks that you're going to have to pay attention to. Arguably, they are more difficult to maintain because of the mechanical issues, particularly the problems that can happen if the shafts get overloaded, which can damage drivetrains. So you're going to have to, pay attention to noises, make sure things are greased and inspected, change oil, clear drains, grease motor bearings, and things like that. But obviously, if you have one of these, you should have an O&M plan for them. If you don't, please develop one, because your system can break down pretty quickly. And obviously, this is a non-existent list. You're going to want to pay attention to filter media and under drains and all the rest of that as well. So we're actually a minute over time, and I am just about finished. We've got one more poll question. Actually, why don't we just skip this and jump straight to the questions? I'm going to open the floor, and I apologize for going a little bit long here. I'm going to open the floor to questions if we have any. And I do want to remind everyone that we are sort of doing a regular office hours process with this as well. The grant that provides the funding to do these webinars also provides funding to do technical assistance. So AJ and I have made a point of it to try and be around at least every Tuesday in the hours that are listed there. So we're Mountain Time, so 10 to 11. If you want to talk to us about trickling filters or anything else related to wastewater treatment, feel free to reach out. Just email one of us and we'll set up a Zoom call for you. If these times don't work, obviously, we'll set something up that does. But this is sort of some time that we've dedicated to being available. So with that, I don't know if we got any questions. If we do, let us know. And AJ and I will try to answer.
All right, James, so we did get a couple of questions. This first one, I believe, was already answered. I think that maybe this person asked before you answered it, but I'm just going to go ahead and read it anyways. Would the BOD loading be a function of the surface area of the media?
BOD loading functions of the surface area of the media. So let's go back to that formula. So this is what we're looking at. So with BOD loading, you're actually looking at the volume of the media. I'm sure there's a way to calculate it by surface area, but typically what you're looking at there is pounds of influent, BOD flow, and the volume that it's occupying. So the volume essentially of the basin that the media is in. The hydraulic loading rate, on the other hand, is what's related to the surface area. So same parameter, a little bit different.
All right, and next question. Is there economic value in the film of the nitrogen fixing films?
I do not know the answer to that question. Some of it is going to be sloughed off, obviously. So it's going to be, biomass that gets moved through your solids handling process. AJ, do you have any idea about the answer to that?
Would you repeat the question?
Yeah, is there economic value in the film from the nitrogen fixing films?
I think that's really going to depend on what kind of resource recovery material could be used, and if it's involved in your solids handling and incorporated into compost. So I think those two are the main things. I'm not really sure. It's probably kind of like a novel idea. Honestly, I think most of the time it's just kind of allowed to settle and removed. But I think that material is probably high, or it is definitely high in nutrients, so it could be used in compost material in your solids handling. And then I know there is some research into different forms of resource recovery from that kind of stuff. But I don't know if anything's ever specifically looked into trickling filters, especially because they are becoming, you know, they're getting kind of phased out.
Awesome, thank you. And the next question is, please explain how the microbiology gets established during the startup or commissioning of these systems, and how long does it take for the microbes to get established?
AJ, you want to take that one? It'll happen naturally. I know that.
Yeah, typically what you use is you're using wastewater that is already being used for this process, that already has those microbial families in there and organisms in there, and you seed the media, which means basically like you're using it, you're running it over there. They're going to establish, you know, colonies and attach to the media. In terms of a time frame, I'm not positive about that. That might be something that we'd have to like research and get back to you on.
Yeah, it's going to depend, you know, some of the information I was looking at, because there are instances when you will essentially have to flood a trickling filter, for example, to get rid of, you know, macrofauna and flush it out. And it can take several days for the system to recover from something like that. But as AJ pointed out, you know, part of recirculation is reseeding. So typically in an operation like that, you would, you know, either you know, you're not going to kill everything off that's in the basin, so it's going to grow back on its own, or you might reseed it using recirculated water from either that basin or from a parallel running system.
Perfect, thank you. And then the last question, do hybrid systems that use aerated sludge basins with suspended filter media share any qualities with trickling filters?
They do, and you know, it's kind of the same idea. You've got some microbes free floating, but you've got essentially a resident population of microbes that are sitting or attached to those floating media. Again, you know, this was meant to be an overview. There's not enough time, and I think we've got another webinar coming up on activated sludge, and we will probably include that discussion briefly in there. But yeah, that is kind of the same sort of process. It's hybrid because you've got essentially a resident population that's always staying in there. The shearing action is different because, you know, the pieces are floating around inside the basin, and that's, you know, the mechanism, and them knocking against each other is a mechanism that sort of regulates the biofilm. But yeah, that is effectively the same kind of process. It's just going on inside a basin that also has activated sludge in it.
And we did get one more question. Are the solids coming from a TF or RBC system different from those of activated sludge plants? Thinking here of effluent sand or anthracite media filtration after the secondary process.
AJ, you want to jump in on this? I mean, I think it's effectively the same or similar stuff, but the volumes are usually significantly different. I think there's typically less biomass coming off, but then again, your trickling filters are usually used for lower BOD rates. So some of that might be a factor of the fact that you're just feeding less food into the microbes, but pretty similar stuff.
Yeah, I mean, go ahead and say that again, please. I need to hear some of those details.
Yeah, so the question is, are the solids from a TF or RBC system different from those of activated sludge plants?
I believe they are different. I think fundamentally it's the same kind of like microbes, but just based on how they grow and how they like slough off, I believe they're different. Now in terms of those exact specifics, again, that would probably be something we'd have to look a little more into.
Yeah, but either way, you need clarification after both of those processes because there are going to be you know, solids in the effluent coming out of there.
Awesome. Well, thank you, James, and thank you, AJ, for sharing your expertise with us today. Following this webinar, each of you will receive a follow-up email with the slides from today and a link to the recording. We also ask that you complete the webinar evaluation following this webinar so you can let us know your thoughts on today's session. This will help us plan out future webinars on topics that are important to you. Thank you so much. We hope to see you guys at future EFCN events.
Thank you, and thanks for sticking with us. Sorry I ran over time.
Thanks, James. Thanks, AJ. Bye, guys.
Thanks, guys. Bye.